Thanks everyone here. So today my talk is going to be about the Hamiltonian geometry on b-symplectic manifolds, following the work of Guillemin, Miranda, Pires and Scott. So a b-symplectic manifold is, first of all, a Poisson manifold with Poisson bracket, and this can be written in terms of a bivector. We use this X to denote the Poisson bivector. Using this notation, then we say that a Poisson manifold is symplectic or log-symplectic if it's even dimensional, and if the n weight of itself actually gives a transversal intersection to the zero section of this canonical line bundle. And then the transversality gives us the intersection to be a codimensional one subtorus, and this is called the singular locus of the b-symplectic manifold. And the two-dimensional case was first studied and classified by Radical in 2002. And it turns out that the b-symplectic manifold is not far away from the symplectic manifold. And for example, there is also the Darboux theorem for the b-symplectic manifold, such that the bivector can be given as a standard non-degenerate bivector like this, far away from the singular locus and near the singular locus. Then there is a mild degeneracy, and you can write the bivector in such standard form. Dualizing that, we can just talk about the two form, which will be closed, and then this will be similar to the Darboux theorem in the symplectic case, such that far away from the singular locus, then we have the symplectic form written locally to be the standard one, and as the singular locus, then the closer to form can be written in this way, such that there is a mild singularity, and this will be the log of z. And this is the Darboux theorem of b-symplectic manifold. And we can actually look at some examples. So the simplest one is just the sphere with now the omega defined to be dh over h, which d theta. H is the height function, and theta is the angular. And then this is going to give us a b-symplectic form with the singularity at the equator. So I'm going to use the red color to denotes this singular locus. So we call this Z, and then we have the manifold itself with the b-symplectic form omega. And this singular locus is also a nice manifold as described by the work of GKM in 2014. What it says is that near this singular locus Z, the b-symplectic form can be written as this way: the log of a defining function Z, which a closed form alpha plus a smoothly defined two form, and this will be this alpha and omega will be on the singular locus, the Z. And therefore, we can consider this triple, the Z, equipped with the closed one form alpha and the closed two form omega. And this, so here we have a b-symplectic. And then this triple is going to give us a cosymplectic structure, in the sense that if we take the weight product of alpha with omega, then this is going to be a volume form. And this is called cosymplectic manifold. And since alpha is a closed one form, then the kernel of alpha is going to define a codimensional one foliation. And we can take any leaf of this foliation, say a leaf here, we take L, and this L equipped with this two form, this closed two form omega, now is going to be so L omega. This is going to be symplectic. So given a b-symplectic manifold, we will be automatically given a cosymplectic structure on its singular locus, and this will be of dimension 2n, this 2n minus 1, and this will be of dimension 2n minus 2. And on this singular locus, there will be symplectic vibration on the singular locus. And in the rest of the talk, we are actually going to compare the Hamiltonian geometry among these three guys, the b-symplectic and cosymplectic, and then the genuine symplectic stuff. And it turns out that if the leaf is actually compact, then the singular locus Zi is going to be a vibration over S1, so it's going to be a mapping torus.
To what extent are omega and alpha independent of the defining function?
Right. It's not independent, but we can, but it does not differ too much. It might differ the log of a smooth function, and that one will not have singularity if that smooth function does not vanish at the singular locus.
So the one form should only change up to a function, right? Because otherwise
right.
the foliation is not.
Right, but but we can make sure that to choose such compact leaf. Yes. Right, I'll omit some technical details, but this is the thing that I want to use. And from now, I'm going to assume that those leaves are compact, so that we will have this mapping torus structure on the singular locus. And because of this log function, and then later on, if we want to do the Hamiltonian geometry and define the moment map, then we have to allow the log singularity to be part of our consideration of the functions. So here is definition of the b function, which are those functions defined smoothly away from the singular locus, but possibly it has some log singularity at the singular locus, and then so this could be constant times log of a defining function and then plus a smooth function. This is the set of b functions that we are going to consider, and with the help of this b functions, then we should be able to define the Hamiltonian torus action together with the moment map as the usual definition in the symplectic case. So we just require the T action to preserve the b-symplectic form, and then we say that this is a Hamiltonian if this contraction is actually exact, so that the primitive function is in the set of b functions. So it's going to be smooth away from the singular locus, and it might have some log singularity at the singular locus. And as usual, in the symplectic case, we will also have this mode map from the manifold to the dual line algebra, and this will possibly has log singularity at the singular locus. So the definition is same as before, except that we now allow some mild singularity near the singular locus. And then the final definition that we are going to use is the modular weights. So now if we are given a Hamiltonian action, then it's going to preserve the b-symplectic form. Therefore, it preserves the singular locus and preserves every component of the singular locus. So we will have a natural action from the torus to a component of the singular locus. And then we can choose any orbits and then consider the natural action from the torus to the orbits.
Chen, are you assuming that the T action is not preserving the foliation, but that you have one vector that is transverse to the foliation for this T action?
Right. It's actually the modular vector field. Right.
So you are making that as part of the hypothesis that the T action is going to have one transverse.
Oh, I'm not going to assume that.
You're not to assume that.
Yeah, because I'm going to deal with either it's going to be transversal or non-transversal. I'm going to do both of the cases.
Okay.
Yeah. And then consider any such orbits and consider the map from T to the orbits. So now, previously we have we have a nicely defined one form of this cosymplectic manifold Z. Then we can pull back this one form to the torus, and since this is going to be invariant, so it's actually sitting inside the dual algebra, and this is called the modular weights of this singular components, and we will denote this to be Wi. The importance of this modular weights is as follows. The modular weights is going to measure the singularity of the moment map, and this can be seen as if we go back to this description, the T log Z, which alpha plus omega I. This alpha I is going to be the one form on the Zi. And then now if the weights has non-trivial pairing with the torus, then when we do the contraction, we will have the log Z coming out as primitive function. So there will be log function, log singularity in the moment map. And if the pairing with alpha is 0, then we won't have this part coming out to be in the moment map. And that's what we mean by the modular weights is going to measure the singularity of the moment map. And here we have the definition of the modular weights for every components of the singular locus. But it turns out that they are very closely related, as in the theorem of Guillemin-Miranda, Pires and Scott. So we have two cases. Either all the modular weights are 0, or the modular weights are non-zero. And if the modular weights are non-zero, then this is the case pointed out by Victor that we will have the torus action also. There will be one direction transversal to the symplectic fiber. And in the second case, each component is going to be a product. Previously, this is going to be described as a mapping torus, but in this case, it actually turns out to be a component, and every component is going to have either one or two. But now every component, after deleting the singular locus, is going to have one or two Zi's as boundaries, and all these weights are just multiple of each other. And one example that we can do here is we can actually, instead of looking at this one, we change the two forms a little bit. For example, if we consider dh over h squared minus 1/4, which d theta. Now this can be written as dh over h minus 1/2 subtracts dh over h plus 1/2, which d theta. So this form is going to have singularity at when the height is 1/2 and the negative 1/2. So instead of having one component, we will have two singular components, and we're going to draw at when the height is 1/2 and when the height is negative 1/2. And those are log singularity. So this will be d log something, d log of another thing. So this is in the definition of b-symplectic manifold.
Wait, there's never monodromy? In each Ci is Li times S1? It's a Cartesian product?
Yeah, it's actually going to be a product. Because, right, so in their proof, what they did is that, so if there is such, if the weights are non-zero, then there will be a direction of the torus action. So there will be S1 act on this Z, and that S1 action is going to give you a actual splitting into a S1 components. So there will be S1 action on this Z so that we can actually have the products. And then now if we want to know what are the weights, the modular weights of this two singular locus, then we just look at the sign here. So as the singularity of the 1/2, so we have the positive sign. So
Did you assume that the zi's are within the region that the action is free? Was that an assumption?
I'm going to assume like effective action. Maybe
No, but
it doesn't have to
do
be
you insist that near zi the action is free? Is that assumed? Or
near the
near
Z.
the zi, yeah.
Okay, Z.
Is that an assumption? You want to use the circle action to trigger this?
Right. Perhaps I'm not sure if it's free, but you can actually spin out this product. Maybe you have some finite stabilizer. Right. So that's their theorem describing that. And in this case, so the weights of the first components, probably I is going to be +1. We just look at the sign here, and so here for another component, so we call this Z1, and here Z2. The weight here, W2 is going to be -1 by looking at the sign here. So we have this the weights with different signs, and that was this was also from this example. He explains what are these weights when they bounce a components in the n-z. So if this two, the Z1, Z2, they bound the same open manifold in outside of the singular locus, and they will differ by a negative sign. So these are all parallel with each other, and hence, if we look at the kernel of these weights, because they are multiple of each other, then the kernel is well defined, and they define the same codimensional only subalgebra. We denote TZ, and because of we will have some nice assumption on the fiber to be compact. Then it turns out that the TZ is going to be integrable, and this TZ actually is going to give us a codimensional 1 subtorus. And we will talk about this a little bit more later. And the main theorem of the work of GMPS is the Atiyah-Guillemin-Sternberg Convexity theorem in the b-symplectic case. And we will divide our discussion in two cases. The case one is when the modular weights are 0, as we remarked before. The modular weights measure the singularity. Now, if the modular weights are 0, then there are no singularity, and the moment maps are just as fine as the symplectic case, and then so they proved that if we consider the moment image, then the convex envelope of the moment image of the critical points, the fixed points, is same as the moment image of the M, and the moment image of any singular locus, any component of singular locus, and the moment image on its symplectic fiber. And in the second case of when the modular weights are not 0, then we can consider the previous splitting. So we defined the codimension 1 the algebra to be killed by this weights. Then if we consider this subtorus action, the modular weights are going to be restricted to be 0 on this subtorus, and then this gives us back to the previous case of a 0 modular weights if we consider this subtorus action, and then we will have now the same convexity property with respect to this subtorus action, and if we consider this this new moment map by projecting to the TZ dual. Now, if we go back to the original moment map, then what we have to do is to take components outside of the singular locus, and then we just do the same type of arguments in the symplectic case, and then it can be proved that the moment image of this component is also convex. And the idea of the proof is that, so for example, in this case, if we take these components bounded by this two components, then we will have this cylinder. Let's call this W. This is going to be open, and it has the boundary Z1 and Z2. And then the technique here is to do the symplectic cutting near the singular locus Zi. And the symplectic cutting is to replace the boundary by the quotient of the boundary by the S1. So we are going to replace Z1 by Z1 modulo S1. And then this is going to collapse the boundary to be a manifold. And in the case of the b-symplectic manifold, this is going to collapse. The Zi is going to collapse into its fiber Li. So in our drawing, we can do. In this case, this is going to be a two-sphere, and in the arbitrary dimensional case, the upper one is going to be the symplectic fiber of the Z1, and then L2 is going to be the symplectic fiber of the Z2. So this is going to be the symplectic cutting for these components near the singular locus. And now this is going to be a symplectic manifold, and then we can use the convexity theorem of this manifold then to prove that now the mu of omega is also convex, because the moment image of the symplectic cutting is convex, and then we can just extend this to the infinity. So that's the idea of the convexity theorem in the b-symplectic case. And inspired from this, we can summarize a slogan here. So when we discuss the Hamiltonian geometry of a b-symplectic manifold, we need to divide the things in two cases. In a zero modular weight case, then everything will be as nice as the symplectic case, because the zero modular weights means that there is no singularity, and then still the b-moment map share the same nice property as in the symplectic case, that when you consider any critical submanifold, the indices will be even, co-indices will also be even, and then this nice properties is going to make sure that those nice results given by Morse theoretical arguments in the symplectic case will also be valid in the b-symplectic case if the modular weights are zero. And the second case, if the modular weights are not zero, then the Hamiltonian geometry of this torus action on the b-manifold will be now related with the Hamiltonian geometry on this symplectic cuts that we describe here. So you take every open components by deleting the singular locus and then do the symplectic cuts. So this will be symplectic manifold endowed with torus action, and we can translate the theory on this symplectic manifold to the b-symplectic manifold. And that's the slogan. And then in the rest of the talk, what I'm going to do is basically to open a standard textbook in symplectic geometry and then look for the b-symplectic version of every theorem in the textbook of symplectic geometry. And before we dive into the details, let's gather the Morse theoretical properties of the moment maps, and I'm just going to walk you through all this. This will be very similar to the symplectic case. For example, if we have the modular weights to be zero, then, as we said, the moment map does not have singularity. This will be well defined and smooth everywhere. And then we will have the T action on the symplectic leaf. Here, yeah, it's going to So there will be torus action induced on this symplectic leaf, and then the moment map will be just a restriction to this leaf. And then the fixed point set is going to be the same as the critical point set. And also, if we look at the fixed point set, if we take any components of the fixed point set, then the restriction of the b-symplectic form is going to give a b-symplectic structure on the fixed point set. And at each components in the fixed point set of this fiber L, then this can be extended with 2 dimensions higher to be a fixed components in the M. And so these are relations between this fixed components. So the dimensions will differ by 2, and then they will have the same indices, the same co-indices, and all of these indices, co-indices are even. And this is the reason why the Morse theoretical results in the b-symplectic case when the modular weights are 0 will be as nice as the symplectic case, because all these indices are even, and then most of the arguments in the symplectic case will carry out to the b-symplectic case. And now, if the modular weights are not 0, then as we discussed before, we can consider this splitting into a subtorus, and then the subtorus is going to have 0 modular weights, and this goes back to the previous case of 0 weights, and then we can also take out every such open components outside of the singular locus, and then do the symplectic cutting, and then apply those more theoretical results in the symplectic case to the symplectic cutting, and then translates the results back to the symplectic manifolds. So there will be induced Atiyah action on the symplectic cutting, and then with a nicely defined moment map, and this will agree with the original manifold and the original moment map quite a lot, except at near the singular locus. And then they will also have some relation between the fixed point sets. So these are the basic, more theoretic properties of the B moment maps. And now let's try to find a b-symplectic version of some interesting classical theorems. For example, the connectedness, and the connectedness is closely related with the convexity. And what we can say is that when the modular weights is 0, then we can take any moments, any A inside the moment image, and then consider the level set. So this is a level set in the B manifold M, and we can restrict this to a component of the singular locus, and restrict this to a fiber of that singular locus. This will be non-empty and all connected. So this is as we saw in the symplectic manifold, the case, the connectedness is equivalent to the convexity of the moment image, and this will be the case when the modular weights are 0. And if the modular weights are not 0, then we take this open components outside of the singular locus, and then consider the level sets inside this open manifold, and this will also be connected. The proof is that we just consider the singular cuts of this open components, and then the connectedness of the symplectic cut is going to lead to the connectedness of such level sets. And then the next important thing that we can do is the reduction. And since we have already seen the connectedness of the level sets, take any level sets, we can consider the quotients by the torus, and then this will be stratified space if the if the value is not regular, and if the torus action is not free, but we can still use the idea of a Schaumar and the Neumann to consider this for any value in the moment image, and then the levels, we can stratify the level set according to the orbit type, and then project this orbit types to the quotients, and then the quotients is going to be given with a stratification, and it will be endowed with cosymplectic forms as same as the symplectic case. Not only we can do the stratification of the level sets of the manifold M, also we can do the stratification to restrict it to the Z and also to the simplified L. So we will get stratified symplectic space, and this will be the stratified singular locus of the cosymplectic space, and also this will give the fiber as stratified symplectic leaf. And then if we move the moment image a little bit inside the regular chamber of a moment image, then there will be the Duistermaat-Heckman theorem that the change of this reduced cosymplectic form can be measured by this pairing, so A1 minus A0, and then with the first triangles of this fibration, supposing that this is actually a fibration of a torus fibration. And then we can also consider the Duistermaat-Heckman measure by computing the volume of this reduced space. And in this case, the b-symplectic form has log singularity, so it might not be integrable. And then according to results of Geoffroy-Scott, actually we can take a b integral even when this actually has some singularity, but it's still integrable. There's some nice definition of that. And because the difference of this symplectic forms is given by this one form, then when you take the integral, this is going to give you a piecewise polynomial, as also same as in the symplectic case. So this is when the modular weights are 0, and then we can consider the modular weights when it is not 0. So as in the Snowden, what we can do is we can still take this open components and then do the symplectic cuts, and then try to get the reduction of this symplectic cuts. So we take any level sets in the symplectic cuts of this components, and then same thing as before. If we have this moment images in a regular chamber, and suppose this fibration is actually a torus bundle, then we can consider the C1, and then this pairing is going to give you the difference between two nearby reduced forms. And then also the Duistermaat-Heckman measure given by this piecewise polynomial. So we see that there is very nice b-symplectic case of the reduction and the Duistermaat-Heckman theorems.
Are the things on the left in that display forms or the numbers or cohomological? The thing in the middle, yeah.
Here?
What are the guys on the left? They're differential forms, or they're
These cohomology classes or potential
or
forms?
cohomology classes?
Oh, cohomology classes.
The omegas are.
Yeah, I should be careful with this. Yeah, this should be cohomology classes.
And the omega on the second display, that's a form. The usual volume. Some of these omegas are Comanche classes and some. Yeah, that's,
Yeah, so in the integrationists, think of this to be cohomology classes.
But the right-hand side of the middle display is C1 is a Chen class, or it's
yes.
so it's being paired with a vector.
What is, yeah,
Yeah, it's going to be a dual, the algebra value two form.
So the Chen class of a torus bundle?
Yeah, a torus bundle. Chen class of a torus bundle. So it's going to be the algebra value two form. And then we can take the pairing with the elements inside the inside the moment image, which is in the dual algebra. That's how the pairing works.
Oh, I see. So, I mean, you write C1, but it's more like some sort of total chunk class.
Right,
But,
right.
yeah, okay.
Right. So it's going to
I
be
mean, it's vector value,
yeah.
basically. It's
the algebra value goes two form.
Okay.
Right. And then you can take the pairing. Right. And so after this, we can do some calculation of some topological invariants. For example, the fundamental groups. And according to a theorem of in 2003, suppose so in the symplectic case, suppose we have a circle action, Hamiltonian circle action with a moment map, say F, and if we consider this,
Is this Wheelie?
yeah, right, and then
Lots of these.
right. And if we consider this n super A to be all the stuff below A, and also consider the reduction at A, then the following fundamentals are isomorphic to each other. So we will have the pi 1 of n is equal to the pi 1 of this guy, of everything below A level sets, and the pi 1 of the reduction, and then send the pi 1 of the minimum manifold and the maximum manifold. And applying his calculation of fundamental groups, we can also do the symplectic case. And the idea of proving this is that we just do the more theoretical arguments. So take any direction of the moment map, and then you just go from the bottom to the top and see what happens when you pass
There's
through.
something here, by the way, that the modular weights are non-zero or if modular weights are zero.
Oh, so his theorem is for symplectic case. It's a symplectic manifold, and
Oh,
I'm
that's
referencing-
on the symplectic.
yeah, I'm referencing the symplectic case.
Relays
Yeah.
result from 103.
Right.
Okay.
And then I'm going to apply this to the
Yeah,
b-symplectic.
that's her result.
Right.
Yeah, okay, I
Right.
understand.
And the idea of the proof is to use the more theoretical arguments, and then you try to see what happens when you pass through every critical manifold. And it turns out that it does not change the pi 1. And then you will have all these fundamental groups to be isomorphic to each other. So if we apply this to the b-symplectic case, for example, we also need to divide the discussion in two cases. If the modular weights are 0, as we remarked before, modular weights 0 means that there is no singularity of the moment map, and then the more theoretical arguments work exactly the same as the symplectic case. So
Yeah.
in the b-symplectic case, if the modular weights are 0, then we will also have the pi 1s of both of the things to be the same. And here we are considering circle action, but this is extendable to torus action. But for simplicity, let's just talk about the circle action. And we have all this identification of pi 1s. Now if we move to the case of non-zero modular weights, then we just do almost the same arguments like here. We take an open components outside of a singular locus and then do the symplectic cuts. And on this symplectic manifold, there is an induced canonical torus action, and it will be Hamiltonian. And then we apply this theorem to this case to calculate the pi 1 of a reduce the space of these components, and then it turns out that this is going to be equal to the pi 1 of any symplectic fiber of the singular locus. and slightly more, but I'm going to skip this. So we will have various identification of pi1s by using the Morse theoretic arguments. And besides the fundamental groups, we can also use the Morse theoretic arguments to calculate, say, cohomologies. And we are going to more interested in equivariantly formal torus action. And by equivariantly formal, we mean that an action in such a way that the equivariant cohomology defined using this Borel model is going to be a free polynomial module. And equivalently, this means that the natural action, the natural map from the equivariant cohomology to the ordinary cohomology is surjective. And we will be interested in this equivariantly formal action mostly. And then the equivariant formality will be guaranteed in the two following cases. The first case is the modular weights when the modular weights are 0, and this is the best case. Whatever works for the simpler case will work in the modular in the 0 modular weights case of the b-symplectic manifolds. And if the modular weights are non-zero, then there might be another chance in this case, so that the equivariant formality still holds. It's when there is a open component outside of the singular locus with only one boundary. Things like this. It means that you can actually stack up. You can stack up all these open components vertically, and using this vertical lining, we can do the Morse theoretic arguments with respect to this vertical lining, and then still make things work. So we will have these two cases such that we still have the equivariant formality for the torus action on b-symplectic manifolds. And if we have this equivariant formality, then those famous theorems should be also true for the two cases. For example, the kernel injectivity, surjectivity, and then the Jeffrey-Cohen-Gilman residue formula, and also Tonner-Weizmann description of the kernel of the kernel map. All this classical theorems in the symplectic case has to be worked in the equivariant or informal setting. And if we can guarantee the equivariant formality, then all these theorems will work in the b-symplectic case. And so I just explained some ideas of how to make this work. So the exact expression will be literally like
I think
word by
still
word.
in the T act with B moment map, then the action is equivariantly formal. Well, I mean, you're considering the modular weights non-zero, the modular weights.
Right.
But these are all the possibilities. So you're saying everything is equivariantly formal.
There is a one more possibility when the modular weights are non-zero. So it's the case that I think in the classification there might be another case. Say for example, if we consider the torus.
But in the first case, the modular weights unequal. Suppose you have a symplectic manifold. You don't always have equivariant formality.
Symplectic manifold, I do think you have the equivariant formality.
Under some assumptions. Well, okay, go on. Under some assumptions on the T action. Go on. Yeah.
I think
It
it's
is.
true, right? Should have the
Okay.
formality.
But,
Right, and then there might be another case where every component has actually two boundaries, like in the torus case, and if we consider the b-symplectic form to be d theta 1 over sine 2 theta 1, which d theta 2, where the theta 2 is this direction, and then theta 1 is that direction. And then we see that the singularity is when the theta 1 is 0, half pi, and 3 half pi's. And then the singular locus is going to be a circle here, a circle at half pi, a circle at pi, and there's a circle at the 3 half pi's. And in this case, those components, they have, all of these components have two boundaries, and then they're connecting like a loop. They cannot be stacked up like a line. And this is when the more theoretical argument might break down, because it does not line up. And the thing that I'm particularly interested in is the GKM-type theorems. And this theorem proved by Guillemin-Sternberg in 2004 regarding the Hamiltonian action on simply manifold tells us that suppose we have a generalized definition of the GKM condition. In the original GKM condition, they assume the fixed point sets to be isolated. And in this generalized definition of a GKM condition, it's not necessary to have the fixed point sets to be isolated. This can be non-isolated, and the GKM means that if we look at the isotropic weights, then these isotropic weights are not only distinct, they are actually pairwise linearly independent. And then the theorem of Victor and the Holm is that all these connected components take any connected components inside the fixed point set, and then all these connected components, they are diffeomorphic to each other, and so we can denote this by a universal, a fixed one, say F. So that's the fixed point set. And as for the one skeleton, which is defined to be the fixed point set of the codimension 1 subtorus, this can also be thought as the union of dimension 1 orbits. This is going to be a union of P1 bundles or sphere bundles. So we can talk about the north section of the sphere bundle and the south section of the sphere bundle. And because of this, then there is still a nice definition of a GKM graph. What you can do is you can take every vertex to be a component, and since the one skeleton is given by a union of P1 bundles and P1 bundles, so you take a south section represented by one vertex and a north section represented by another vertex. So this H is going to be a P1 bundle or a sphere bundle, and then this gives us an H, and then just connect to any other nearby ones. Then this is going to form a GKM graph. And their theorem in the simpler case is that now if you calculate the equivariant cohomology, then this can be given as a tensor product of a combinatorial data with the cohomology of the a connected components of in the fixed point set. Now, if we apply this GKM-type theorem to our b-symplectic case, we will see that the results are just literally the same. And we will start with the simpler case with modular weights 0. And this will be more or less the same as the simpler case. What we will consider is to calculate the equivariant cohomology of the manifold M and a singular locus, and also a symplectic fiber. It turns out that if we look at the fixed point sets of M and the ZI, Li with respect to the torus action, then those components will be diffeomorphic to each other respectively. So the components, all the connected components here are diffeomorphic. All the components here are diffeomorphic, and there also. And this, so we can take any connected component F in a fixed point set of N, and then we can take the intersection with Zi. This is going to give us the connected components inside a ZT and then take the intersection with the Li, it gives the connected components in the LT. And then we just apply the same arguments as in the previous case of symplectic manifolds. Then we will actually get a GKM graph for all of the three manifolds, the simply manifold and the cosymplectic manifold and the simply fiber. They share the same GKM graph, and then the equivariant cohomology can be written as the tensor products of this combinatorial data with a connected components in the fixed point set.
Do you know that these intersections are connected?
Yeah, it can be proved. Yeah.
Oh, that's
Right. Yeah. This will be part of the results. It can be proved that these are connected. And so this is still in our slogan that if the modular weights are 0, then the results are just going to be as nice as the simpler case. More or less, you can just literally apply whatever you get in the simpler case to this case of modular weights to be 0. And if the modular weights are non-zero, then we will do this symplectic culling, and then apply the GKM theorem in the sense of getting a home to this symplectic culling, and then get a GKM-type theorem to the symplectic culling, and then translates the results back to the manifold itself. So we have this condition. Suppose the weights are non-zero, and then suppose we have the torus actions to be GKM in the sense of a element at home. Then the results that we can get using this symplectic culling, what we can do is that this time we will get a GKM graph for the manifold M, and the GKM graph constructed from the singular locus, and this will be used for the symplectic fiber Li, and then we can also get that this equivariant cohomology is going to be this tensor product of a combinatorial data with the cohomology of the fixed point set. And the thing in this non-zero modular weights case is that now those connected components in the fixed point set on M and in the fixed point sets on Li, they will be not only diffeomorphic within those two categories, two families, they are also diffeomorphic with each other. So they will share the same connected components in the fixed point set, and that gives the same F here, but different GKM graphs. The idea is just to do the symplectic culling and then apply the Guillemin-Sternberg theorem to the symplectic manifolds. And now so we discussed quite a lot of classical results in the symplectic case proved using the more theoretic arguments. And there is still a missing case. The Guillemin-Sternberg, the quantization commutes with the reduction. And now we have already seen that the reduction makes sense for the torus action on b-symplectic manifolds. The only thing is that now we need a well-established geometric quantization theory, and I think this is still ongoing project, joint project of Miranda and Weizmann. And Jonathan explained some ideas in yesterday's talk. So if the theory works out, then we should also expect this the quantization commutes with a reduction in the b-symplectic case. But we need to get such a theory first. All right, I think that's my the stuff of my talk, and then still just remind ourselves of the slogan of the Hamiltonian geometry on the b-symplectic manifold. It's that if the modular weights are 0, then whatever the nice results on the symplectic case will also make sense in this case. And if the modular weights are not 0, then we just need to do the symplectic culling and then relates the cut space with the original space itself, and then we will see that the Hamiltonian geometry of these things are closely related with each other. Thank you.
Any questions or comments? No. And let's thank Chen again for holding this talk. We will resume in half an hour. Last but not least. And I will probably be stranded here.
My flight has been delayed by 2 hours.
My flight is an undefined status.
Dear.
It's supposed to now leave at 7 p.m. instead of 5:30, but the incoming flight doesn't arrive until 8, and that's assuming that it leaves at... I might want to do that.